Morning, I am Nihal Morsi, a master's student at Ain Shams University, Faculty of Engineering Architecture Department. I'm here to present a paper titled Computational Design for Architectural Space Planning of Commercial Exhibitions, a framework for visitors' interaction using parametric design and agent-based modeling. This paper is authored by Nihal Morsi, Dr. Shaima Kamel, Dr. Hanan Sabri, and Dr. Ayman Asif. Commercial exhibitions are temporary events that provide great opportunity for business owners to sell their products, gain exposure, and interact face-to-face with their customers. The factors that affect user experience are layout configurations that affect the traffic patterns and environmental cues by other visitors. The research problem here is how can designers change layout design for these transient events in a fast and smooth manner and evaluate the layout configuration so that they can provide the best visitors experience. The layout planning for commercial exhibitions starts by dividing aisles and corridors, then the remaining spaces are allocated for booth division. High traffic zones include zones near the entrance, near main aisles, within the inverted triangle space, from the entrance, near landmarks, and at the center of the exhibition space. Crowding is one of the most important social factors that affect visitor behavior. It has an inverted U shape, which means it can have both a positive and negative effect. It can lead visitors to popular spots, but also it can hinder them from seeing exhibition stands, and it can lead them to continue moving instead of engaging with exhibition stands. Agent-based modeling is a computational model that simulates dynamic interaction between autonomous agents. These agents interact with the environment according to predefined rules. They are extensively used in architectural applications such as to simulate pedestrian movement, for evacuation studies, for form finding, and to evaluate circulation path. The research aim of this paper is to propose a framework that uses parametric modeling and agent-based simulation to help architects enhance the layout of commercial exhibitions and evaluate visitor interaction. The proposed framework consists of two parts. The first part is to parametrically represent the exhibition layout. The second part is to simulate the visitor's movement using agent-based modeling. The agent-based simulation parameters are first the environment that includes obstacles, stops, and dimension of the space, the agents that have a number of interests, the number of agents in the space, the vision, the radius, and abandoning time. Simulation settings such as duration of the simulation and the output data. Of course, the parametric definition of the layout is what defines the environment parameters. Then the simulation is run, the data generated, visualized, and analyzed. This leads us to know how we can apply changes for better configuration scenarios. The model is divided in three parts: the entrance area, the booth at the border, and the central booth zone. Model parameters include the dimension of the exhibition space, the border booth widths, and the points where it is cut so that it allows for service entrances and exits. The widths of the interior area booth, the number of vertical aisles, the number of horizontal aisles and their widths, the widths of vertical main aisle and the widths of the horizontal main aisle, also the number of booths and their division, and the central area and the entrance area dimensions. Model outputs are specific for the application of simulation: the outline of the booth groupings, the division of the booth, and access points to each booth. The environment for the simulation includes walls as obstacles, the booth grouping as transparent obstacles, and access points as interest points, and both the entrance and exit points. The agents here represent the visitors. They have a vision of 360 degrees and a radius of 0.3 meters. The software used for simulating visitor movement is PETS Improve. It is based on the social force model. The agents move according to a number of forces. First, the target attraction force, the repulsive forces from obstacles and other agents, and noise force to avoid bottlenecks. This program is an add-on to Grasshopper in Rhino. The application of the framework starts with a generic case study of an exhibition space of 90 meters wide and 110 meters of length. Proposed scenarios are mainly concerned with the configuration between horizontal and vertical aisles, adding horizontal aisles, then adding a main vertical aisle, then adding both main vertical and horizontal aisles. Also, it is proposed that the space is distributed in zones that represent interest zones for each group of visitors. The simulation algorithm starts with defining agent stops, entrances, exits, and interest points. Then the agent profiles. The number of visits is set to 10 and visiting time to 60 seconds. Simulation settings include the population, which is 1500, and a duration of simulation of 20 minutes. The data visualization takes the data output and visualizes it for analysis. For the results, we see that the cumulative trajectory taken at the beginning of the simulation shows that the configuration with vertical aisles enables the agents to reach most of the booth in less time and also better distribution of trajectories. And the visualization of the number of agents per cell map, this also confirms the first observation. We see that for scenario 1A and scenario 2A, there are fewer dead spots and the agents are simply better betterly distributed in a better manner. Although most scenarios have bottlenecks in crowded areas. Visitors count per booth shows that the zones near the booth near the entrance have the highest visit count, with scenario 1A having the highest visit count per booth in all scenarios. Also, we can see that when the average of visitor count per booth per zone was calculated, zones such as scenarios such as 1A, 1B have very high visitors count, but scenarios such as 2B have a good distribution between zones when it comes to visitor count. It was observed that during the simulation, the agents that have interest in the zones nearer the entrance would stop for their interest points, which would hinder the other agents that needed to go further back to visit their respective zones. This also can be something that happens in real situations. The advantages of using agent-based modeling is that it's very flexible. Also, it can be expanded by adding it to other models. The idea of producing the layout in 2D and simulation and running the simulation in the same platform also reduces a lot of time, as the simulation usually needs very precise drawings and sometimes it needs some modification. The usual process was that you would get the 2D drawings and then input them to a separate simulation software. However, agent-based modeling comes with sets of limitations. It's hard to verify and validate the experiment due to the lack of data we have and also how hard it is to get this data. The abstraction level is another issue. If the model is too simple, you can miss important parameters. If it's too complex, it would be hard to understand and hard to run, as agent-based modeling is also quite computationally expensive. There comes the question of, can we really model human behavior. Humans have different reasons, both rational and irrational, to their behavior. However, there are certain trends. So we can say that the simulation results can be used as learning models other than be used for forecast and predictions. The resulted um, the results showed us possible dead spots and possible crowded spots. These coincide with the literature. Also, we can see that aisle widths and the configuration of the layout has a role in how the footfall of visitors is distributed, which also coincides with the previous literature. For future research, we can try different scenarios with different entrances, maybe regular shaped spaces, different booth groupings, um, changing the interest zone distributions. Thank you.